Hi everyone. Today we'll be discussing about the concept of radius of curvature, and this is applicable to any mathematical function that you can represent on a coordinate system. So basically like parabola, which is more frequent for 11th and 12th students. Probably in waves chapter, when you come across this concept of transverse waves, which is going to be a sinusoidal function, you'll be learning when we discuss again in waves chapter. So these kind of mathematical functions which are looking like curves when you plot them. So for these curves, how are they changing their direction? The change in their slope, that particular concept is being explained by this technological term called radius of curvature. Right? So today we are going to see how is this radius of curvature expression derived mathematically. So let's get into the details. Let's consider a random function f of x. It could be a parabola, it could be a sinusoidal function, it could be any function that is changing its direction basically, right? So any mathematical function is given by y is equal to f of x, right? We all are aware of this. So let's talk about slope of any function. Usage of your differentiation, right? So slope of any random function, slope of a y versus x graph is given by dy by dx. So we all are aware of it. So differentiation of y is supposed to be differentiation of f of x with respect to x, which is what we are going to write it as f dash of x. So this part we are very much confident in, right? And those who are not aware of differentiation, do not worry. I am going to give a separate video on differentiation alone, starting from the basics, which is the first derivative principle. All right, don't worry. So let's get into the details right now for this radius of curvature. So let's say this y of x is looking like a random function, a curve basically. So I would like to plot a y versus x graph. So since I want to show that it's changing its direction, I'm showing that it's changing its direction somewhere like this. Right? So to how much is this particular curve changing its direction at a particular location from that instant to the very next instant? That is supposed to be explained. So, say for example, somewhere over here is its imaginary center, let us say, right? So, from that particular point to the next point, say for example, like this, somewhere over here. This is its imaginary center, probably, we can assume. Okay. Now, I want you guys to imagine that you're, you know, focused on this particular region. Imagine that you're zooming into this particular region, and I'm going to draw in detail of this particular region alone, right? So let's imagine that particular region alone is being drawn over here. That's how it's going to look like. So if I now break it down into parts, probably like an x component and a y component, this is going to be the x component of it, and this is going to be the y component of it, right? So that region might be having certain length, and I'm going to consider that the length over there is some dl, and this y component is supposed to be like some dy. The horizontal is supposed to be like dx. We all know this particular line, say for example, with the x-axis is making an angle theta. The slope at that particular instant is given by what? Tan theta. So this is known to us. And tan theta is given by dy by dx. Right? So the point over here is finding the radius of curvature. So I know or we know that the length of an arc is given by L is equal to r times of theta if theta is in radians. Right? So if theta is in radians, this is the case. But if theta, like say for example, is in degrees, you have to make the conversion and then do it, right? But here, the length of the arc is supposed to be only dl because this is the only length that is used over here. So dl is supposed to be the length, and r is supposed to be the radius of curvature of your curve length dl over there. So that r is supposed to be found out. So dl times of d theta, which is supposed to be the small angle that is subtended over here, is what you can imagine, right? So this is done. So you need to find r. R is your objective, which is your radius of curvature, right? So once we have all this, can we not write r is equal to dl by d theta. Can be done. So once you have written dl by d theta, I want you guys to make a very small modification to this. I want you to write it as dl by dx theta by dx. Okay. So why? I'll let you know in some time. So let's say this triangular part is there. Look at that triangular part where dl is looking like the hypotenuse, dy is looking like the opposite, and dx is looking like the adjacent. So we know from Pythagoras theorem that the hypotenuse length whole square is dy square plus dx square. So just divide with dx on either side. So it's going to look like dl by dx the whole square is dy by dx the whole square plus 1. So if you're interested in finding what is dl by dx, you're just supposed to be writing square root of dy by dx the whole square plus 1. Right? You have a dl by dx over here. So I want you to use it over here, which is supposed to be root of dy by dx the whole square plus 1 divided by there is a d theta by dx. The only thing is you need to find what is d theta by dx, right? But you know that tan theta is dy by dx. So if tan theta is dy by dx, differentiate this expression on either sides with respect to x once again. So it's supposed to be what? Secant square theta d theta by dx, which is supposed to be d square y by dx square. Alright? So I need only d theta by dx. So you just have to find out what is the differentiation. So it's supposed to be d theta by dx is equal to d square y by dx square times of 1 by secant square theta. So once you have come to this conclusion, I want you to use it over here. Right? R is going to look like it's root of, root can be taken as a power of 1 by 2. So it's 1 plus dy by dx the whole square whole power 1 by 2. If y is f of x, you just substitute the f of x in the place of y. If it's an x square thing, you substitute what is x in place of y, x square. And if it's something else, you just substitute that. So you'll get the functions. And at that particular location, wherever he's asking you, substitute the coordinate values over there. Radius of curvature value. So that is it. So we are going to see an example in the future, probably when I come to waves topic. There's one numerical in advanced what can be discussed over here. So I'll bring it up at some point of time in the later part. So this is it. This is radius of curvature. You're going to see multiple such applications probably somewhere whenever there is an advanced question coming up in the future. All right then. So see you in the next video with something which is really interesting. Thank you.